Read the scenario, study the graph, and try to answer these questions on your own before proceeding with the movie. We're first asked to state Ohm's law in words. Ohm's law states that the potential difference across a conductor is directly proportional to the current through the conductor at constant temperature. In effect, Ohm's law states that a resistor's resistance is constant as long as temperature is kept constant. And that's because resistance is the ratio between V and I. According to Ohm's law, if, for example, we have a resistor of resistance 2 ohms, as long as we keep the temperature of the resistor constant, its resistance will stay 2 ohms, even if we increase the potential difference across the resistor. As we increase the potential difference across the resistor, the current strength through the resistor will increase in the same proportion, keeping the ratio between V and I at 2, or we could say 2:1. In other words, keeping the resistance at 2 ohms. It's important to note, however, that Ohm's law should actually not be called a law, because a law is meant to hold true for all known conditions. However, that's not the case with Ohm's law. Ohm's law is only true for ohmic conductors. Non-ohmic conductors don't obey Ohm's law. Now remember that direct proportion means the more by the same factor. As one variable is increased, the other increases too by the same factor. So if the potential difference across an ohmic resistor is doubled, let's say, then the current strength through it would also be doubled. By whatever factor the potential difference is increased, the current strength would increase by that same factor. And direct proportion results in a straight line graph when we plot the two variables against one another. And that's what we see here. We have two straight line plots of potential difference against current strength. X and Y are two different arrangements of resistors. In each case, as we increase the potential difference across the resistors, the current strength through the resistors increases by the same factor, resulting in a straight line graph. Now we're asked what the gradient of this graph represents, and we're asked to calculate the gradient of graph X. We know that gradient means how steep the graph is. Rise over run. Change in Y over change in X. For this graph, what does rise, what does change in Y represent? And what does run, what does change in X represent? And from that, what do you deduce that the gradient of this graph represents? The Y or vertical axis represents the potential difference across the resistors, and the X or horizontal axis represents the current strength through the resistors. So the gradient represents V over I. What is V over I? We know that resistance equals V over I. So the gradient of this graph represents the resistance of the resistors across and through which the measurements were made. For graph X, what is this value? We can use any triangle to get the same answer for X's gradient, since X has a constant gradient. It's a straight line graph. But the easiest triangle to use is probably the largest one, and so let's use that one. For that triangle, Y final is 3 volts and Y initial 0 volt. So rise, change in Y, is 3 minus 0 equals 3 volts. And for this triangle, X final is 0,75 amperes and X initial is 0 amperes. So run, which is change in X, is 0,75 minus 0 equals 0,75 amperes. 3 volts divided by 0,75 amperes equals 4 ohms. So that tells us that for the arrangement of resistors in X, the total resistance is 4 ohms. Now work out the resistance of the arrangement of resistors in Y. 0,75 volt divided by 0,75 amperes equals 1 ohm. Remember that the question told us that in both X and Y we have two resistors, R1 and R2. In one of these, R1 and R2 are connected in series, and in the other they're connected in parallel. Which fits with which? Is situation X the series or the parallel connection? Is situation Y the series or the parallel connection? Try to answer this yourself before you proceed. To help yourself to see what you need to see, remind yourself what the total resistance is of each of X and Y, and remind yourself of how total resistance is affected by adding resistors in series and in parallel. And also think of how one calculates the total resistance of resistors in series and in parallel. Adding resistors in series increases total resistance. We can think of resistors in parallel like a thicker pipe, which makes flow easier, lowering effective or total resistance. Adding resistors in parallel decreases total resistance. So the lower value total resistance, Y, must correspond to the parallel arrangement. So now we're ready to answer the final question. Determine the resistance of R1. The question could just as well have asked, determine the resistance of R1 and R2. Try to answer this yourself first. Give the formulae for calculating total resistance for resistors in series and in parallel to help you. The total resistance for the series arrangement is 4 ohms, and this must equal the sum of the resistances. So we know that R1 plus R2 equals 4 ohms. The total resistance of the two resistors in parallel equals the product of the two resistors divided by their sum, and we know that this must equal 1 ohm. We've already seen that the sum of the resistances equals 4 ohm, so we can replace R1 plus R2 by 4. And we know that R1 times R2 divided by 4 equals 1. From this, what do we deduce about R1 times R2? R1 times R2 also has to equal 4, so that 4 divided by 4 equals 1. So what could R1 and R2 be so that both their product and their sum is 4? Now there are various possibilities, but one of these possibilities is very easy to see, and that is if each of the resistors is 2 ohms. Two 2 ohm resistors in series have a total resistance of 4 ohms, and two 2 ohm resistors in parallel have a combined resistance of 1 ohm. For extension, you could then apply your mathematical skills to work out other possible combinations of R1 and R2, which would result in the same kind of effect.